So we are now here in the chapter 5 of electronic devices and circuit theory, the bipolar junction transistor AC analysis. So in this chapter we are going to examine the AC response of the BGT amplifier by reviewing the models most frequently used to represent the transistor in the sinusoidal AC domain. So BJT transistor modeling, so it is a model of a combination of circuit elements which is properly chosen that best approximates the actual behavior of a semiconductor device under specific operating conditions. So for example, yung AC equivalent circuit is already determined na. The schematic symbol for the device can be replaced by this equivalent circuit, and the basic methods of circuit analysis applied to determine the desired quantities of the network. So there are two models commonly used in the small signal AC analysis of the transistor. So these are the RE model and hybrid equivalent model. So in time, the use of the RE model became the more desirable approach. This is because an important parameter of the equivalent circuit was determined by the actual operating conditions rather than using datasheet values. So the RE model is just a reduced version of the hybrid model, which is used almost exclusively for high frequency analysis. So this model also includes a connection between output and input to include the feedback effect of the input voltage and the input quantities. So here in these figures, we can see that our capacitors, which are with very small reactance at the frequency application, so the C1, C2, and C3, were replaced by a low resistance or short circuit. So after the removal of the DC supply at yung pag-insert ng short circuit equivalent sa mga capacitors, we can now redrawn for the small signal AC analysis, so shown in these figures. And so if we establish a common ground and rearrange the elements, we can see that our R1 and R2 will be in parallel, and our RC will appear from the collector to emitter. So now moving on to the RE transistor model for the common emitter configuration. So here we can see our equation for the input side, the ZI will be equal to VI over IB. So this will also be equal to VBE over IB. So for solving VBE, VBA is equals to IA times RA. So this is equal to IC plus IB times RE equals beta times IB plus IB times RE. So simplifying, this is equal to beta plus 1 times IB times RE. So our ZI now will be beta plus 1 times IB RE over IB. Cancel our IB, so our ZI will be beta plus 1 times RE. So as we recall, that the diode resistance is determined by RD is equal to 26 megavolts over ID. So using the subscript E, because the determining current is the emitter current, so this will result in RE equals to 26 megavolts divided by IE. Now let's move to the early voltage. So this is gonna discuss the intersection that was first discovered by James M. Early in 1952. So in reality, the characteristics don't actually have the ideal appearance like what we have kanina, yung figures na discuss natin. So rather they have a slope. So dito gagamitin natin yung slope. So we know that slope is just equal to the change of y over the change of x. So this will be equal to the change of IC over the change of VC. So overall, this will be equal to I over R sub O. So we must remember that as the base current increases, the slope of the line increases, so resulting in an increase in output impedance with increase in the base and collector current. So for a particular collector and base current as shown in this figure, the output impedance can be found using the following equation. So our output impedance will be equal to change in V divided by change in I equals to VA plus VCEQ over ICQ. So for the situations where the early voltage is not available, kung wala yung early voltage, so the output impedance can be found from the characteristics na ginamit natin kanina, yung the slope na formula. So mag-derive lang tayo dun until we get the equation change in VCE over change in IC. So here for our common base configuration, we can see that it is just similar in many ways to that of the common emitter configuration. So in general, The common base configurations have very low input impedance because it is just essentially simply RE. So this also means that the output impedance R sub O will typically extend into the megaohm range. So the output impedance is quite high. Now let's move to the common emitter fixed bias configuration. So note that our VI, or the input signal, is applied to the base of the current, while our VO naman is off to the collector. So in addition, we can recognize that our I sub I, or the input current, is not our base current, but it is our source current, while our I sub O naman is the collector current. So the small signal AC analysis begins by removing the DC effects of the VCC and replacing the DC blocking capacitors C1 and C2 by short circuit equivalence, so resulting in this figure in the right. And now, substituting the RE model to the common for the common emitter configuration from this figure in the right, the result will be this next figure. So the value of RE must be determined from a DC analysis of a system, and the magnitude of the RO is typically obtained from the specification sheet of characteristics. So assuming that beta, RE, and RO have been determined, will result in this following equation. So this is based from our previous figure. So here our ZI is equals to RB in parallel with the beta times RE. So for majority situations is yung RB natin is greater than, more than a factor of 10 sa beta times RE natin. So our ZI now will be equal to beta times beta times RE. So this is for the input impedance. Now for our output impedance, so we are just going to recall the output impedance of any system, which is defined as the impedance Z sub O, determined with when V sub I is equals to 0. So when V sub I is equals to 0, our I sub I is equals to I sub B, which is equals to 0. So this will result to an open circuit. So the result is the configuration Z sub O equals to RC in parallel with RO. So if RO is greater than or equal to a factor of 10 from the RC, so this will result to, or Z sub O will be congruent to RC. Now for the voltage gain, the resistors RO and RC are in parallel, and so our V sub O will be equal to negative beta times IB times the quantity of RC in parallel of RO. So our IB is equal to VI times BRE. So by substitution, our V sub O will be equal to negative beta times VI times VR over beta times RE times the quantity of RC in parallel of RO. So our voltage gain is equal to V sub O over VI. So this is equal to negative RC in parallel of RO all over RE. Now looking at the phase relationship, as we know that our AV is equals to V sub O over V sub I, which is equals to negative RC to in parallel with RO is all over RE is negative. So the negative sign in the resulting equation for the AV reveals that a 180 degrees phase shift occurs between the input and output signals. So as shown in this figure. So here in this example 5.1 for the network shown in this here, we are asked to determine the RE, the ZI with RO is equals to infinity ohms. Calculate we are going to calculate also ZO with RO infinity ohms. Determine the AV with RO is equals to infinity ohms, and repeat part C and D including RO equals to 50 kilo ohms in all calculations and compare results. And so for A, the DC analysis, to determine the IB, IE, and RE. So our IB is equals to VCC minus VBE divided by RB. So this is equal to 12 volts minus 0.7 volts divided by 470 kilo ohms. And by simplifying, this is equal to 24.0.4 0404 milliamperes. Then our IE, since we already got the IB, this is equal to beta plus 1 times IB. So 101 times 24.04 milliamperes is just equal to 2.428 milliamperes. Now our RE is just equal to our equation 26 megavolts times divided by IE. by substitution, 26 megavolts divided by 2.428 milliamperes, and some simplifying 10.71 ohms. Then for our beta times Re, given that our beta is 100, so 100 times 10.71 ohms is just equal to 1.071 kilo ohms. And our Zi1, which is RB in parallel with BRE, is equals to 470 kilo ohms in parallel with 1.071 kilo ohms by simplifying is equal to 1.07 kilo ohms. Then for our C, the ZO, Z sub O is equal to RC, which is our RC is equal to 3 kilo ohms. And for our AV, which is equal to negative RC over RE, so this is equal to negative 3 kilo ohms divided by 10.71 kilo ohms equals, by simplifying, is equal to negative 280.11. Now let's solve our Z sub O and A sub V, where our including our RO, which is equal to 50 kilo ohms in all calculations. Then we will get that our Z sub O will be equal to R sub O in parallel with RC is just equal to 50 kilo ohms in parallel with 3 kilo ohms is just equal to 2.83 kilo ohms. So versus the 3 kilo ohms, so we can see that it is smaller. And for our voltage gain naman, our AV will be equal to R sub O in parallel with RC divided by RE. So 2.83 kilo ohms over 10.71 kilo ohms is just equal to negative 264.24. So versus the negative 280.11. So we can see here that it is greater than the previous